We are a group of IVDP students, and today we are excited to present our infographic project titled Electrons at Work: How Electron Configuration Shapes Our World. So, our chosen subject is chemistry, and our subtopic is 1.3 electron configuration. In this video, we'll explore how electrons are arranged in atoms, and more importantly, how this invisible structure powers batteries, electronics, or even environmental solutions around the world. Let's dive in. Let's start with the basics.
So, what exactly is an electron configuration? It's the way electrons are arranged in orbitals around the nucleus of an atom. This arrangement follows the rules of quantum mechanics and determines an element's behavior, how it reacts, bonds, and even what it looks like.
To describe electron configurations, we use orbitals S, P, D, and F, each with a different shape and capacity. Electrons fill these orbitals in a specific order, starting from the lowest energy levels and moving upward.
Three main rules that we can use to know how electron fills up energy levels in atoms. The first one is Aufbau principle, which electrons will always fill the lowest energy levels in atom. The second one is the Pauli exclusion principle, which explains that each orbital can only hold two electrons and they have opposite spins. And the last one is Hund's rule. The electrons will fill up the empty orbital first before sharing the orbitals.
There are also some exceptions, like copper and chromium, where electrons shift orbitals for extra stability. This may sound complex, but it's the key to understanding the periodic table and the chemistry of life.
Thanks, Alisha. Now, let's look at how the structure shows up in the periodic table. The table is actually arranged based on electron configurations. Group 1 and 2 belong to the S block. Group 13 until 18 make up the P block. The middle transition metals form the D block, and the bottom two rows are the F block. The period number tells us about the highest energy level, and the group hints at the number of valence electrons. To write electron configurations, we either use full notation or noble gas shorthand, which saves a lot of time and highlights valence electrons. For example, chlorine's full electron configuration is 1s2, 2s2, 2p6, 3s2, 3p5. But in shorthand, it's only neon 3s2, 3p5. Why study this? Because it tells us everything, from atomic size to reactivity, and even whether an element could conduct electricity or form a certain compound. Now, let's look at how this knowledge shapes the real world.
Thanks, Rahma. Electron configuration isn't just theory. It powers the devices and systems we use every day. Let's start with batteries. Elements like lithium, nickel, and cobalt have specific electron configurations that allow them to store and release energy efficiently. For example, lithium's single valence electron makes it lightweight and highly reactive, perfect for fast-charging batteries in phones and electric vehicles. Then, there are semiconductors, which are used in chips, computers, and solar panels. Silicon with its 4 valence electrons is ideal because it can both hold and share electrons, enabling precise control of electrical current. Without it, your smartphone and laptop wouldn't exist. All of these applications are rooted in understanding how electrons behave at the atomic level. This matters globally because lithium-based batteries are powering the shift towards sustainable energy and reducing carbon emissions from fossil fuels. During the 2021 chip shortage, millions of devices were delayed, reminding us how vital electron behavior is to our digital world.
Building on that, let's explore two more global uses. First, catalysis. Transition metals like platinum and iron have incomplete d orbitals, which allow them to temporarily bond with other molecules and speed up reactions. For example, in the Haber process, iron helps produce ammonia for fertilizer, and platinum is used in catalytic converters in cars to reduce emissions. And all these are possible thanks to its electron structure. In air polluted region, catalytic converters reduce emissions like carbon monoxide, which is a major urban health concern worldwide. Next, environmental chemistry. Toxic heavy metals like lead and mercury have configuration that allow them to form strong and harmful bonds in their body. By understanding their electron behavior, scientists can design chelating agents that remove these toxins from water or human tissue. So, electron configuration does not just help us build, it also helps us protect. In countries that experience water contamination, lead exposure continues to threaten this community, especially children.
Before we wrap up, here are some fun and fascinating facts. Did you know that the color of transition metals comes from its d-d electron transition? That's why copper compounds are blue or green. And gold appears yellow, unlike silver, due to its relativistic effects on its orbital. The electrons move faster due to its heavy nucleus. In conclusion, electron configuration might be invisible, but it impacts everything, from the devices we hold in our hand, to the electronic we use, or even the air we breathe. Thank you for watching our video. We hope you have learned something new, and that you now may see the electrons as more than just tiny particles, but as the architects of modern world.